Right. Thank you, everybody, for your patience. Grace Jiang is going to present a tropical cyclone uncertainty quantification for projecting risk in climate change.
So yeah, everyone, I'm Grace, and I'm a current junior here studying computer science. And actually, both other people mentioned on this slide are here in this room right now. Jiang is sitting there, and then Sai is in the back. So yeah, I'm gonna start. So Bangladesh or just say what I worked on. I worked on a learning accelerated approach to risk assessment, specifically on storm surges in Bangladesh. And the reason we're looking at Bangladesh is because of its geographical location as a low-lying coastal delta. It's highly prone to flood inundation. This flood inundation can come from extreme rainfall, but it can also come from more extreme weather events. So tropical cyclones, and that is the area of focus. The reason we're looking at tropical cyclones in Bangladesh is because in the last century, the deadliest tropical cyclones have mostly passed through Bangladesh. And it's a really important issue that we care about. So this is why we are figuring out ways to assess risk that these tropical cyclones pose to the coast of Bangladesh and communities. So Bangladesh faces a lot of perils from tropical cyclones. Because of the excessive wind, tropical cyclones cause storm surges, which are just when the ocean overflows onto the land, and the rain causes inundation. And all of the above cause a lot of property damage and loss of lives. So we want to assess the risk of these perils happening, and I will go more into that, more into what that process is. So first, I'm going to go over the general process of what risk assessment is before going into how I improved on this general process this summer. So risk assessment is identifying likelihood of different extreme weather events and assessing what their impact on coastal communities is. So for example, in the tropical cyclone situation, there are different degrees of tropical cyclone. There might be a tropical cyclone with a return period of 1 year, which just means this is the most dangerous cyclone for the last year. And it has a return period of say 1,000 years. This is a much more dangerous cyclone because in the last 1,000 years, this is the most dangerous cyclone. So with different degrees of cyclones, they pose different impacts. We must look at the kinds of impacts they might pose, and therefore we can develop sustainable solutions. This is a map not of Bangladesh, hopefully it doesn't look like Bangladesh. It's Tampa, Florida. This is an example of different solutions that might be reached looking at flood inundation along the coast and just storm surge levels caused by cyclones. So for one specific cyclone, this might be the best scenario, the red areas you abandon and the black areas you armor. Oh, and risk is always changing as the climate changes. And it's important to assess risk for future climate scenarios now so that we are prepared when the future climate comes. And future climate, there's multiple different scenarios that might happen. So it's important to assess risks for the possible climate scenarios that might be in the future. And here's the current workflow for how this risk assessment process works for tropical cyclones. So we start with these general climate models that are developed by different organizations around the world. And these climate models can be of present climate or different scenarios that might happen in the future. But the problem with the climate models and figuring out tropical cyclone danger from them is they're too coarse to accurately simulate tropical cyclones. A tropical cyclone on a climate model is typically around 1 pixel, and 1 pixel doesn't tell us anything about what that cyclone is or what dangers it might pose to the coast. So we from these climate models, we do a process called tropical cyclone downscaling, which takes a climate model and produces specific tropical cyclone paths that go through certain regions. And after we have these tropical cyclone paths, we run a physically based storm surge simulation, and this is what simulates storm surges along the coast. And we're using storm surges as a measure of how destructive a cyclone can be. Obviously, there's other ways a cyclone can be destructive, but for the purposes of this study, we're using storm surge along the coast as a measure because it's really important. Storm surges do cause a lot of destruction. And after we have the storm surge levels at different points along the coast of Bangladesh, we can risk assess at those points and then develop the sustainable solutions, which an example of was shown on the last slide. There are a lot of different organizations that produce different climate models. And the ones we looked at, there's 2 that we looked at specifically. One simulates present climate, is the ERA5 reanalysis. And it's kind of voted, hopefully the voting is seeable. And reanalysis, what that means is that it's benefited from observations of the current climate. So these models use current climate observations to strengthen them and make them more accurate to what the climate currently is. Another model is a future climate scenario. It's EC Earth 6 SSP 5 8.5. What SSP 5 8.5 means is it's a specific scenario for future climate that assumes the economy is growing, has grown, but the growth is spurred by fossil fuels. So it's a pretty worst case scenario for global warming and carbon dioxide emissions. And there's the 20th century column just means it's current climate, but not strengthened by observations from the current climate. From these climate models, as I said before, we can produce specific tropical cyclone tracks. And this is a map showing some of those that go through Bangladesh. And the reason, you might wonder why go through this whole process of making fake cyclones, synthetically generated cyclones, instead of just taking data from cyclones that we are sure have existed. And the reason is, from observed history, there's not been enough cyclones to accurately produce risk assessment. So for accurate risk assessment, if we want to account for the tails of the cyclone distribution, such as those 1,000-year return period storms I was talking about, you can't just look at the last 100 years and be yes, there's a 1,000-year return period storm in here. You're gonna have to figure out how to get cyclones, more cyclones than nature has produced. And this is why doing it synthetically is the only way. We can't take observations from nature. And additionally, nature has produced exactly 0 cyclones in future climate scenarios. So the only way to accurately risk assess for the future is to produce cyclones synthetically through this process. After we have those cyclones, we run the fluid simulation, the hydrodynamic simulation. And here's a video showing that. So the cyclone, as it goes through Bangladesh and the ocean, it's very pixelated. You can see the wind bars and the tides and water levels. So the reason the water levels flash from kind of hard to see yellow to blue a few times is because the tides change throughout that process. The cyclone also induces storm surge and other changes in water levels on top of the tides. So that simulation is enabled by this underlying computational mesh. This is specifically called a finite element mesh, and all the physics equations are solved on the nodes of the mesh. So yeah, and you can see the nodes there's a lot of nodes near the shore. So the mesh is at really high resolution near the coast. And because of this, there's a lot of computational power required to resolve the equations. And I'll go back to that computation PowerPoint very soon. But first, we know that this method works well because comparing it to historical cyclones and running historical cyclone data through the simulation, the results are very similar. So these graphs show the water levels at 2 different points along the coast. The reason they go up and down even before the cyclone hits land, which is that dotted line, is because the tides change. But the red line is the simulation results where the cyclones change in water levels, and the black dots are observed values, and they match very well. And yeah, so after we run each cyclone track, we will assess the output at each of these 54 stations of what the cyclone storm surge produced was. Most of these stations do not exist in Bangladesh, they're just virtual stations plotted on the map. But there are some locations that also correspond with the red dots that correspond with real tidal gauges that are in Bangladesh. So after this process of simulating the storm surge, we can look at what kind of risk there is for the future in terms of cyclones and storm surge. So based on the red line is that future climate scenario I was talking about earlier, where we assume economic growth is spurred by carbon dioxide and fossil fuels. And the blue line is the current climate. So considering these two scenarios, we're seeing that for example, for a storm with a return period of 100 years, also the stations, the titles are station names, which are named after members of our lab group, but that's kind of side note. We see that 2 of the stations, current return period 100-year cyclone would cause 4-meter surge, and that becomes over 6-meter surge, considering the same type of cyclone in future climate. So these are an example of risk assessments we can do after we have that information. So now I'm going to go into specifically what I worked on this summer to improve the process. So there's a big issue with this whole process at the moment, not necessarily issue, but just downside. where the hydrodynamic simulation requires a lot of computation power. So if, for example, like for the issue of tropical cyclones globally, let's say we want to assess that like risk of tropical cyclones for 5 different climate scenarios, and there are like 10 different models that are slightly different per scenario, and like 5 different sea level rise conditions that are potential for the future. And as I mentioned, the 10,000 cyclone tracks is generally accepted. Like we need this many tracks to accurately assess something to account for the tail ends of the distribution. And for each, like for the climate model, the cyclones that are downscaled from it and the storm surge simulation, each step in the process produces some errors. And to account for like potential errors, we want to like change the parameters of tropical cyclones, like parameter perturbations, to account for these errors. And let's say like Bangladesh obviously is not the only place that suffers from cyclones around the world, so there's a lot more sites around the world that we want to do this analysis on. But multiplying all those numbers together, we would need like a lot of simulations, like a lot of runs of this hydrodynamic simulation. And considering like the amount of power the computer core requires, this running all these simulations would be enough power to drive an electric vehicle to the moon like around 4,000 times. So this is a kind of a waste of power if, well, obviously the information gained through running these simulations is really useful for protecting coasts and human lives down the line, but this is a lot of power, like just used in general. So I'm looking at a way, I looked at a way this summer to reduce this amount of power through machine learning, because machine learning, like basically it's fast and much faster than running a simulation. So the solution is we don't run a simulation on every single track. So for example, let's say we have 5,000 tracks, cyclone tracks, and only some of those are potentially destructive cyclones. The others are like mild cyclones that pass through Bangladesh, and Bangladesh does not suffer that much other than get some rain for a few days. So we want a machine learning model that picks out from these tracks the ones that have high destruction potential. And then we only run the hydrodynamic simulation on the ones that are destructive, because those are the ones that we care about assessing risk for. Those are the ones that the cities, like coastal cities, will need to protect themselves against. So by doing this, instead of having to run simulations on 5,000 tracks, we can run simulations on just a fraction of those and save a lot of time and computation power. So the way this machine learning model is trained is the cyclone tracks produced by cyclone downscaling have 100 plus time steps in it, and each time step is an hour in that cyclone path. So maybe like the first hour, the cyclone's at this location is a parameter in that time step, and then it has like this wind speed, it has this like radius of max winds, etc. So from these 100 time steps, we only care about the ones close to landfall, because these are the time steps that matter for storm surges near the coast. So we decided to extract the first 24 hours before landfall, and those hours, the landfall hour, as well as the 8 hours after landfall. And from each time step, we take 5 parameters, because each time step has like around 30 parameters, most of which probably don't matter, but some of them do matter. And these are the ones that we initially determined we will choose. And in the future, if there are more parameters, we can easily incorporate them just as an additional parameter in the model. And yeah. So we want the machine learning model to take in these tropical cyclone tracks, and we want it to output the storm surges at the stations along the coast. So the output data that we have, or we take, is from each of these 54 stations. The simulation like generates this max water level plot, and we just take like the locations at the 54 stations, the value of this max water level elevation plot, and that would be the max surge reached at that location for the whole cyclone's track. So I'm gonna quickly go over how like a machine learning model works and like how it's trained and then can predict future cyclone tracks. So the specific model we use is like a model off the scikit-learn Python library called XGBoost. And upon initial assessment of a few different scikit-learn like machine learning models, this seemed to work the best. But if we want to improve on the results, we might do like a more deep analysis of which models like work best for our purposes. But with this model, we take like the tracks as input data on training, and then the 54 storm surges at like for that cyclone at each station as output training data, and these two, like we put them into the model, and the model learns or attempts to learn how to like predict the output from the input. And after that, we have different cyclone tracks that we input as testing data, and the model will predict what these surges will be for these cyclones. And then we can assess the accuracy of the model based on these predictions with the output testing data, which are the true values for what the surges those cyclones produce are. So there are, like, I ran 3 experiments that each show some sort of promising result. So the experiment 1 is just showing that machine learning can predict storm surges in present climate, and therefore through this process we can reduce the amount of simulations you would have to run. So the PRA5 data, I briefly mentioned, it's just the current climate data. And from the current climate data, I separate 75% to use as training data. So the current climate data just means cyclone tracks that would happen in the current climate. So 75% of those cyclone tracks separated as training data, and 25% are used as testing data. And this is a random split, so not like the first 75% is training, but it's a random 75% taken out, and 25% used for testing. And I ran 50 trials because there is chance for randomness, where like the 75% used for testing could be a really bad 75%, so that the testing results are not as good. And with the 50 trials, the randomness will be like even out. So the results, like I display as confusion matrices, and what the thresholds mean are, so basically we have all these cyclones. For any of them, if they produce a storm surge that is greater than 1 meter, say, at any of the 54 stations, then it gets placed as above that threshold. So if a cyclone has a storm surge that's produced at any of the 54 stations that's above the 3 meter threshold, it gets placed as, yes, it is above the 3 meter threshold. And then the predicted is the machine learning's prediction, and then the column, or this side, the actuals are the actual values. So we're gonna look specifically at the 3 meter threshold case, because a lot of barriers that exist in Bangladesh that protect against storm surge are 3 meters tall. So once a cyclone storm surge reaches past that threshold, that's when it can really start causing damages. So looking at the 3 meter case, we see that 84% out of the entire cyclones that are above the 3 meter storm surge threshold, 84% are captured by our machine learning model, which is a large majority of them. And out of the, like, we have this information. So the machine learning model takes the cyclones and tells us these are the ones it thinks are destructive, these are the ones it isn't. So we run a simulation of the ones we think, like the machine learning model tells us, yes, these are destructive. Out of all the simulations we run, 81% is the amount of actual destructive cyclones that will be caught. Meanwhile, if we ran this simulation on just all of the tracks without knowing this information, we would have to like run a lot of simulations, and only 24%, which is the sum of the first column, or the sum of the first row, yes, would be actually above the threshold. So we have 81% like running this way of the simulations are above the threshold, while running simulations on all the data without knowing this information, we would only only 24% of the cycles would be destructive, which means we have like a large reduction in the amount of simulations we run while capturing 84% of the total amount of destructive cyclones. So experiment 2, the purpose is to show that machine learning can predict storm surges in a future climate scenario. So in this case, the model is trained on all the current climate data, like a bunch of cyclone tracks, and tested on cyclone tracks for SSP 5 8.5 scenario. And comparing the results from this experiment to like the previous experiment, the 3 meter threshold, the results are actually a little bit better. And first, this might like raise red flags, like, hold on a second, this doesn't make sense. How can we predict the future better than we like assess the current climate? But that's with a few caveats. So the cyclone tracks use, like the SSP data cyclone tracks are already adjusted for future climate conditions. These are cyclones produced through downscaling in the future climate model. And their like wind speeds, all sorts of parameters have changed already to reflect that. So it's not like the machine learning model is like taking cyclones in current climate and being like, this is what the cyclone would be like in the future. It already knows that information from the data. And the storm surge simulation run doesn't account for sea level rise, it just assumes no sea level rise. So those are the results that we're comparing what the machine learning model like outputs are. So like there are a few caveats, like sea level rise is not considered, and the storms are already assumed, like in the SSP data, the storms already are in future climate scenario. But it is still very promising to show that like the machine learning model has potential for predicting what storm surges will result from cyclones in the future. And experiment 3, basically I reduced greatly the amount of training data the model was trained on and still ran it on the future climate data. So from the results, like we see that running the model, like training the model on just 20% of current climate data produces results that are very similar, like almost as good as if we ran it on, trained the model on all of the current training data. And like the machine learning model does train a bit quicker if it's given less data, but the more important reason this is important for us to know or useful is the training data. Like the training data we use to train the model, we must run the simulation on all that training data. And that's because to train a model, we need to know the outputs. So we have a bunch of tropical cyclone tracks that we say, okay, these are the ones we're going to use to train the machine learning model. But to train the model, we also need to know the storm surges from those tracks. And our current way of knowing the storm surges from those tracks accurately is through the hydrodynamic simulation. So imagine we wanted to like make the perfect machine learning model. Then obviously we take every single tropical cyclone track that has ever been synthetically generated and train the model on all of those, and then we'll be like, yes, now it is a perfect machine learning model that can predict every synthetically generated cyclone track. But the problem is we had to run all those simulations to for the machine learning model to be trained. So it's very beneficial that machine learning is able to make these assumptions that are not, or make these predictions that aren't that much worse, greatly reducing the data. So yes, the conclusion here is that we can insert machine learning into the current workflow for predicting storm surges and tropical cyclones and risk assessment. And machine learning accelerates sampling storms for target distribution. And here we just accelerated the sampling of extreme storms. There are also other applications of this machine learning model. So earlier I briefly talked about how there's uncertainties in climate model, tropical downscaling, storm surge simulation process. Like each step has its uncertainties that we aren't sure if they are accurate with the real world. Machine learning model, we can just adjust parameters a little bit, and in tropical cyclones, put them into the machine learning model instead of the hydrodynamic simulation. And that way we can see how our results vary with these little uncertainties incorporated in a quick way, because we don't want to run so much, for each cyclone track, if we adjust the uncertainties in a couple of different ways, that multiplies the number of storm surge simulations we have to run. And machine learning does the same thing in a matter of seconds versus the storm surge simulation, which takes much longer time. And that is the end of my talk, but if you guys want me to clarify anything or have any questions, I'm opening floor now. Yes.
I'm wondering if you tried also running your machine learning model on any observed tropical cyclone tracks that are in the Bangladesh area. And I guess my question there too is, do you think this is something that once the sort of fuller models have done predictions when there's a storm kind of approaching, if your machine learning can kind of provide a rapid prediction of what people should expect for storm surge?
So right now the machine learning model only predicts the maximum storm surge reached at any of the 54 stations. But when people assessing what people should do at each step of the cycle, it's probably useful to know the whole timeline of what the surge will be at for this point in time versus that point in time. So right now the purpose is just pick out the extreme cyclones so that the simulation can be run for that accurate information. And I bet there's a way to make a model that's more accurate than the one right now. But the one right now is more to accelerate the process rather than be more accurate than the current process. Yeah. Yes.
Could we potentially deconstruct the model to form better or deconstruct the machine learning model to form better like models or systems for tropical storms. Like in what way can we, because sometimes machine learning is like a black box. So in what can we pull from like the model and put into and modify like original equations or models?
I guess like machine learning is kind of a black box. So if we want to like take information from it, we have to like run the information through the model in some way, and we can change aspects of that information. So we can, let's say, make a tropical cyclone have like greater wind speed, or change the location a little bit and see what the model like changes outputs based on that. And maybe this will tell us information about how the model works, but really we can only assume like overall, and there's no way to like deconstruct the model to see what's inside, I guess. Yes.
Thanks, Grace. This is really interesting. Can you go back to like the slide with the mesh and like all the nodes? I guess I just noticed that like the nodes cluster more towards the coast, and I was wondering if like there's a reason for that.
Oh yeah, so near the coast is where we care the most about water levels. So because the mesh is more clustered, we have like more accurate assessment of the water levels near the coast. And meanwhile, in the middle of the ocean, it doesn't matter, like 1 meter, or like it's 1 meter this way in the middle of the ocean, because 1 meter next to it. Nobody lives there, so it probably doesn't matter that much. When you're near the coast, like just a 1 meter difference can be somebody else's house.
Oh wow.
Yeah.
I guess like how would like what would you have to do to apply this to other places that aren't Bangladesh? Like, do you need to make a node for like other places as well?
I think if we wanted to apply to another location, we have to make this mesh for that other location and then run the cyclones through the simulation. But I did not do this simulation. John Shaw is the one who deals with the simulation aspect.
Do you have a sense on how sea level rise is going to be important in the future? Because you say it's not considered. You said maybe it's a 4 or 6 meter storm surge. Is that going to add a lot, or?
Sea level rise depends on a lot of things that we aren't sure of at the moment, because like baby policy will say carbon dioxide emissions are illegal now, and then sea level rise will not be as severe as if we just let everyone use as much fossil fuels as they want. But sea level, like there's basically no way it stays the same. It will definitely rise, we just don't know the amount. And the simulation right now doesn't consider that. Does I have an answer to the question?
So I think in Bangladesh, the more important thing is local sea level rise, because the land surface is changing enormously in contrast to global sea level rise. The coastline of Bangladesh is such that you could do simple bathtub type linear methods to incorporate the effects of sea level rise. So I expect a model like this to work quite well. But the issue in Bangladesh is not global sea level. It's, in the coast, Bangladesh is actually gaining land. But internally, because it's a delta, there's too much going on, and that I don't think the model would work too well considering all the effects of local sea level rise. And that requires a different investigation, I would say.
I think you had a question?
Oh yeah, I was just wondering, did you run into any sort of pitfalls of applying machine learning? Like, did the algorithms you tried kind of work out of the box easily, or like did you ever get sort of nonsensical results that you then had to adjust?
Oh, I mean, there was one thing that I tried, which was, so I'll go back to this. This is a much simpler version of the original thing that I was trying, which is, the original thing is I split the original data into 5 parts, and then there'd be like 5 models. First model is trained on the first part and tested on the second part, and the misclassified cyclones from that model are put back in the training data. And then like on and on, kind of like you strengthen the training data based on which cyclones are misclassified. But that didn't really yield any better results than just running the model on less data. So could be the way that we're selecting the data, like that way isn't different than randomly selecting the data.
Okay.
But I think there's all sorts of things that happen in machine learning, you aren't sure why. And it's like you just have to come up with another idea to see if like this way will produce results that are more useful.
Yeah, I was also wondering about like if you saw, if the machine learning predicted sort of discontinuous storm surges at adjacent sites or anything like that, any non-physical features or.
I didn't really look specifically like at that data. So I'm not sure.
Okay, fair enough.
Yes.
I think earlier questions touched on the implications that this model has for understanding the effects of climate policy on the occurrence of tropical storms. So I was wondering what you saw as like potential things we could learn about climate policy, or maybe like potential effects that we could predict.
Yeah, so I guess I only looked at one potential future climate scenario, which assumes like a general story of policy, and then look at the other scenarios. But like with different future climate scenarios, if you did the analysis, you would see like this is a type of tropical cyclone given this type of scenario where like this general policy is followed. Yes.
Go to the slide where you have the two curves, blue and red curve. Yeah. So, do you want me to butt in or?
Or I can talk. So like, I guess what I worked on specifically wasn't to look, like this risk assessment process would kind of answer your question, looking at the risk for different future climate scenarios. And you'd be like, this scenario, the cyclones get a lot worse. So this is a downside of following this policy. But what I was doing this summer was improving upon the storm surge simulation step. So like from these improvements, we can more quickly assess these kind of questions, like address these kinds of questions, but it doesn't like necessarily help us better address these kinds of questions. It's just we can make these conclusions faster if we speed up the storm surge process.
And this is only one part of the story. For example, in Bangladesh, you can see in every case that the risk of sea level of surge has really gone up. I mean, those two curves are very far apart. So if you take the same return level, it's really moved a lot. Most of the embankments won't be able to stand a 100-year return period storm if they can do it today. But the story there is much more complex than Bangladesh because land is subsiding on the inside, the embankments are old. It won't even take a 100-year storm to blow through the embankments. And we haven't looked at issues like salinity, which is even more important. And because the way the embankments are built, a lot of the salt water just rides up because of tidal amplification all the way into the inland. And so these are very complex interactions of infrastructure with storm surges. From a policy point of view, one of the things we are coming up against is, should they even have built these boulders? Could they just have flooded the land, and if it had remained aerated properly, there would have been good sedimentation. People could have adapted using their historical methods. So we're kind of asking those questions. Some of that is enabled by this, but it's a very complex set of things that we need to straddle to take a result like this into policy. There's still a lot more work to be done.
Okay, hopefully you learned something.